adjust that as we go through this. So we already talked about what to include. Those are the kind of bulk ideas behind what should show up in your title, except hydrochloric acid is sulfuric acid. Unfortunately, you will see typos like this in these PowerPoints because I'm really quickly throwing them together to get some kind of formatting behind what I tell you in recitation, as opposed to me just writing it up on the boards. When I write it up on the boards, I for sure will get it correct. Okay. As far as the report goes, as always, title with everything, results and calculations, and then discussion and conclusion. So with this experiment, the discussion and conclusion, you'll find in most experiments, actually, they're relatively short. There isn't a whole lot to state in them. One of the things that makes it a little bit more difficult or misleading with the discussion and conclusion is that you're supposed to tie in what you talked about in your introduction back to your results and calculations. Well, if you don't have an introduction, how do you tie it? It's not really easy to do. Okay? So what we'll go through with each experiment is kind of talk about what things should show up in the introduction. You can then decide of those what things can you bring down to the discussion and conclusion. Do they directly tie to your results? Okay, that's ultimately what we're looking for. So why do we end up doing this experiment? The whole point is to get the enthalpy for this reaction. So then it still comes back to, well, why do I want the enthalpy for this reaction? In a lot of cases, that can come down to scale. If we want to scale this experiment up, say move into industry and run this experiment, because we want to make, for the sake of argument, let's say we want to make hydrogen gas. Okay, well, if we run this experiment and we scale it up 1,000 times, do we need to be concerned about the temperature that's also given off, or the heat that's given off in the course of this? So having an idea of the enthalpy for a reaction can help us come up with safety factors to allow for the reaction to occur appropriately and safely. It can also allow us, once we have that reaction, we can use Hess's law from 151 and start to add up other reactions with enthalpies to determine the enthalpies of unknown reactions. Say perhaps ones that we can't run an easy experiment for. Okay? In my opinion, this experiment is actually fairly interesting because of that correlation that we just briefly talked about. We're trying to ultimately relate volume to energy. Okay, so it's a really bizarre relationship between those two. In my opinion, that's kind of neat. So I would actually kind of classify as why we're doing this. It's just kind of fun to see that we can do it. Okay? I know, you guys won't find it fun, but I think it's interesting. Okay? Next part is how. So this is where we're starting to get into the mathematics a little bit and trying to understand the individual pieces. One of the first things that we're going to rely on is the first law of thermodynamics, which is what? Energy is not created or destroyed. If we put it into an equation, what we could end up saying is that the energy released by a reaction plus the energy absorbed must equal 0. Okay? So that's what we relied on when we looked at Hess's law, when we did the calorimeter in first semester. We're going to rely on that same law this time around, except we're going to have to change some of our equipment. Or we're going to change some of the equipment, which means we change some of our assumptions. This law holds only for a closed system. Okay? What do we mean by a closed system? Well, the system is ultimately what we get to define. So if we look at the universe, energy is always conserved. The energy of our reaction goes out into the universe and is absorbed by the universe. We will get 0. Unfortunately, can we monitor all of those places that absorb that energy? No. So instead of looking at our system as the universe, we want to isolate our reaction into our own miniature system. That miniature system, we can now effectively say that our energy is equal to 0. Okay? When we did this in 151, okay, we ran our reaction, which was our energy released, and we then obtained the energy absorbed. What was our system? What absorbed the energy when we ran the reaction in 151? Okay? It was the environment around it, and we effectively said that that was water. Okay? How do we determine the energy absorbed by the water? What was that? Okay, we related that to the change in temperature, but what are the units on temperature? Units on temperature, Kelvin or degrees Celsius. Okay, so that's not an energy term. The energy term units would be joules or kilojoules. So just the change in temperature doesn't help us. What else did we need to know? I know this is pulling at the dregs of your memory. What was that? Specific heat. So a C term, that related the joules of energy per gram times the degrees Celsius. What was the last term that we needed to know? The mass. How much water was actually present to absorb that heat. So that's cool. We could stick a thermometer in there and measure the change in temperature. One issue with the thermometer. Why does the thermometer allow us to see what temperature happens or what temperature changes there were? We can see the thermometer bulb move, right? What is motion attributed to? Energy. If there's motion within the thermometer, what is the thermometer doing? Absorbing energy. There's an extra term that would show up in here. The absorption of energy by the thermometer. Did you calculate that? No. So when you ran that experiment, you already had a source of error. You're monitoring the change in temperature, and that energy loss to the thermometer, you're assuming is zero. Okay, you're saying it's super negligible, which in most cases it's pretty close to that. Okay? So that was kind of our idea with that. So the reason I brought up this experiment and our thermometer is that we can see that that energy can be released in other forms that we can't monitor. For those of you that did do this experiment, you did the styrofoam cups. How many styrofoam cups did you use? You used 2 more than likely. You had 1, and then you put another one around it. Why'd you use the second one? You were trying to keep all of the heat in the reaction. Okay? As you ran the reaction, did anybody happen to grab the calorimeter, the styrofoam cups, while it was running? Did you feel any heat coming through the styrofoam? Typically, you do feel heat coming through the styrofoam. What does that mean? Where's that heat going? Into your hand. Your hand is absorbing heat. Did you account for that in your calculation? No.
So is the styrofoam
Okay.
cup, right?
Huh?
Well,
So is the styrofoam cup officially. So there's a lot of places where that energy is lost. So that's ultimately one of the things that's going to cause all of these experiments to be problematic when looking at these energy transfers, is that energy can be transferred to a variety of things that we aren't monitoring. Okay? So let's say perhaps we decided to do this experiment to get rid of that energy transfer. So instead of monitoring a change in temperature, what we're going to do is use our calorimeter, but we're going to make it isothermal. What does isothermal mean? No change in temperature, which means we don't have to worry about the thermometer bulb changing, and if the temperature never changes, we won't see heat being transferred to the equipment. Okay? So that's nice. We simplify our equation. Except, what's the problem? As our equation is set up, to determine the heat absorbed, I need to know a change in temperature. If the temperature never changes, what happens to the equation? Pretty useless. Okay? So in an isothermal situation, we have to come up with another way to monitor this. Okay? The lab procedure tries to go through and explain the second law of thermodynamics and explain how that directly correlates to this. Anybody know what the second law of thermodynamics is? Looks like some of you wrote it down. Since you wrote it down, let's take it a step further than that. What do any of the words mean in the definition that you wrote down? What is entropy? How do you measure that? It's not heat. Heat is more directly correlated to enthalpy. That definition, first off, we aren't even going to evaluate until much later in the semester. That's chapter 17, I believe. So we haven't even talked about it yet. Even then, I don't directly see how it's useful to look at for running any of the calculations in this experiment. Okay? So as far as the second law of thermodynamics go, what can we do with it? We can just ignore it. Okay? So let's just not worry about it. So what we want to do is go back to our initial circumstance. So the second law doesn't give us an answer to solve this problem. Okay? We need to come up with some other way to determine the energy absorbed in this case. So that energy must go somewhere. Okay? Where does that energy go? What absorbs that energy? How can we get something to absorb energy but not change temperature? We can do a phase change. Okay? So in the course of this reaction, what we're going to do is have the energy released by our reaction go in to melt ice. So change our physical state from ice, solid water technically, to liquid water. Okay? We don't see a temperature change there during that phase transition. If we want to, we can go to an easier one to evaluate and look at the liquid to gas transition. You take a pot of water, you put it on the stove, and you add heat to it. What happens to the water? Slowly it heats up first, the temperature increases until what point? Boiling point. And then it gets to 100 degrees Celsius. You're still adding heat to it. Does the water continue to get hotter? No. What happens? Changes phases into the gas state. So that energy is going into the water, but not going in to increase the temperature. It's going in to break the intermolecular forces holding those water molecules together, the liquid water together. So what we're doing is breaking that force and turning them into the gas phase. That phase transition is isothermal, no temperature change. The ice to liquid transition does the exact same thing. Okay? Ice to liquid, if we were going to look at that energy change, so if we looked at the energy for our phase change, we could change this around, and instead of saying energy, we can say the change in enthalpy. So there's an enthalpy term for that phase change. And we could say, be more specific with the phase and say it's solid to liquid. Of course, that is way too detailed and makes too much sense to write solid to liquid. Instead, we call it the delta H of fusion. Okay? That value is something that we can look up. What it measures, if we look at our units there, is the energy, so joules, per amount of whatever our species is that's transitioning. How do we measure amounts of species? We could go through with moles. Is there another way we could do it? If I asked you to measure some water form or measure some ice for me, would you measure the moles? Could kind of get into volume, but ultimately the easier way would be mass. We looked at a solid. So you can look up, the energy per mass of water. That number is something that you would have to look up. It's a standard for water. You don't have to worry about calculating it. Okay? To get the energy absorbed, okay, we want to know how much water actually changed state. Okay? So our energy absorbed will be equal to the change in mass for the course of the reaction times the change or our heat of fusion, which I guess isn't a delta, but M for mass. Okay. Why mass? It's easier to measure mass than it is moles. If you want to do moles, that works just as well. Okay. That's the change in mass of what? Of whatever changed phases. Okay, so ultimately our ice going to liquid. Okay, so what we could do is set up the reaction, surround it with ice, weigh the ice first, surround that ice around our reaction, run the reaction, take the ice out after the reaction and reweigh it. And we now have a change in mass. That works. What's the problem with that? Has anybody tried to mass ice? We take an ice cube out and we weigh it. It melts. Is it ice anymore? No, it's a mixture of ice and liquid water. So we can't directly measure the mass of ice. That's a bit problematic. So what we're going to have to do is design an experiment that we can somehow indirectly determine the mass of ice, or the mass that went through this phase change. And that's where the rest of this experiment comes into play. Okay? So we just talked about some of these heat terms. Our heat released is going to be equal to the delta H for your reaction. Our heat absorbed, I guess I didn't put, oh yeah I did, there it is. The change in mass times the delta H of fusion. Okay? So how do we measure that mass of ice? So here's our experiment. So we've got an idea on what we want to do for our calculations. Now we'll kind of jump back to the experiment. So what we're going to do with our experiment is we're going to take a beaker. Actually, let me go grab one real quickly. We're going to take our reaction mixture. We're going to fill this beaker with ice. Okay? And we're going to take our cork. We'll put the cork in here, and this cork has a bunch of different things in it. One is our test tube, which is going to be our reaction, where we're going to run that reaction. And you'll notice the test tube goes all the way down into the bottom of the beaker. So now what we can do is say that the ice is now wrapped around that reaction mixture. As the reaction goes, it translates the heat through the glass into the ice. There our ice melts. Okay? Couple other things that we've got here. We've got a pipette on the side. What do pipettes measure? Volume. Interesting. They don't measure mass. That's a bit odd. And we'll come back to that in a second. We can't measure the mass change here. Right? We are potentially have this set up to measure a volume. Is there a relationship between mass and volume? Mass and volume. Density. Okay, so what we can do is look at the density of this species. Okay? So before we do that, sorry, the sequencing on this isn't quite exactly what I wanted. We can measure that change in volume. So in the course of the reaction, what happens? So this will have liquid up in it. Okay? And what happens as the ice melts? Is there a difference in volume for the same amount of ice versus water? Our volume does change if we take the same amount. Okay, so in the course of the reaction, as we change the amount of ice, we're going to change the volume. So what we should be able to do is look at a change in the volume. Okay? That change in volume is due to the change in volume of both the ice and the water in the reaction. Because as the ice melts, its volume should decrease. But then what happens to that water, or that H2O? Where does it go? Instead of being a solid, it goes into the liquid. Now our volume for water should go up. Okay, so what we're looking at is that change for each of those, and to see how that ultimately correlates. Okay? So what's our relationship between our mass and volume? That's our density. The symbol for density is rho. Okay, I've noticed a lot of instructors don't like to use that, but it's what it is, so we should use it. Our density is that symbol. If I handwrite it out, that's how I would write it, just so you get an idea. Okay. So what we can go through and do is say that the change in volume in our experiment is going to be due to the change in volume of our ice plus the change in volume of the water. Okay. Is the density of ice and water the same? No. How do we know it's different? Ice floats. So it's less dense than water. Okay? So we could go through and set up a new equation. Remember, what we ultimately want is the change in mass. That's going to be really important for everything else. So we can now set up a new expression. The change in volume of ice is going to be equal to the change in mass of ice divided by the density of ice. So what we did was rearrange this equation. Yes? Kind of getting some yeses. We'll rearrange that real quickly just to make sure.
Question.
Yes?
For density, where are we getting the mass from? You can't mass the ice.
We're about to get into that. So we know that our volume is equal to mass over density. Okay, yeah, that's one of the things that makes this complex, more complex. So we know that the change in volume, we can now set up this expression. Nice. Ultimately in this, what do we want? We really want the change in mass, ultimately of our ice, because ice is what's absorbing that heat. Okay. Why is the water not absorbing heat? What's that? No, there's water in the reaction. This is an ice-water mixture. Why do we say the water is not absorbing heat? No. There's still ice there, which means what's the temperature of that ice-water mixture? 0 degrees Celsius, which means the water is not absorbing any heat. All of the heat is going into the phase change. As long as there's ice in that reaction, we don't have to worry about temperature going into the liquid. It only goes into the solid. Ish? Okay. So here's this expression. And you brought up an interesting point. What we wanted was ultimately our change in masses, but we said we can't mass the ice. Well, maybe we can mass the water. Okay, except what are we going to run into the issue there? Say we filter out all of the water. In the process of that filtering, the ice is exposed to room temperature air and is still melting, which means we're still transferring some mass over to the water phase. Okay, so we don't have an easy way of calculating those. So if we go back to our terms here, we know the density of ice because we can look it up. Density of water, same deal, look it up. Change in volume, can we determine that? Yeah, that'll actually be on our pipette. Okay, so we can get that. So we tried to set up a system where we could determine the change in mass. That's ultimately what we wanted, but we're now left with the same kind of issue. We still have two variables, two unknowns, with only one equation. Okay, anybody see any ideas how we can get around that?
Can't you mass your water though?
The issue with massing the water is that the ice will still melt as you're trying to filter the ice away from the water. Because you don't want to mass the ice with the water. How are you going to determine the volume of each? Particularly because the ice we've got is crushed ice. That's going to be difficult. We could get it for the water, but the ice is going to be a challenge. No. According to the first law of thermodynamics, energy is not created or destroyed. Is mass a form of energy? Yes. Go back to Albert Einstein's famous equation. E equals mass times the speed of light squared. Energy and mass are directly related. So if we have a change in mass of the ice, that change in mass or that change in energy must be counteracted. There must be a replica of it. Where is that replica? Change in mass of the water. In the course of this reaction, the ice mass does what? Decreases, because it's no longer solid. It's absorbed and become liquid. So that value should decrease. But what happens to the mass of water? It's also going to increase. Conservation of energy, we know these two, when summed, must equal 0. Okay? Why is that helpful? We now have two equations, 1 and 2, with two unknowns. What can we do? Solve and substitute. Okay? I did not show the substitution in this, but these are the two equations that you're ultimately going to work with. Okay? It looks extremely messy, and if you ask me for help, what I will end up doing is rearranging these so we get one equation where we say the change in mass equals all of these variables, and then I would expect you to plug in all those numbers. Okay? As I said, it looks extremely messy and it tends to piss students off more than help them. So I'll leave you to do that substitution. Okay? So these values we can substitute, we'll solve for our change in mass. The densities we can look up. The change in volume we can get from the experiment. So now what we've got to do is see how our experiment measures that change in volume. Okay? Any questions about any of that setup so far? Okay, I know it's a lot and it really doesn't get any easier. Okay, and we'll go ahead and push forward. Determining that volume change. Okay, and this is where it gets tricky. What you're going to measure, we already saw that data table, was time and volume. Okay? When you run the experiment, you'll have this burette filled with the volume all the way up towards the top. Okay? So as a rough guess, which way do you think, what do you think is going to happen to the volume? Probably decrease. Why? Because if it increased, we don't have any way of monitoring it. So very clearly it's got to decrease. Why would the volume decrease? Ice was less dense, so it took up a larger volume. So when we transfer it into the water phase, it takes up less volume, which means our volume decreases. Okay? So when we set this up, we want that volume decrease to be due solely to what? The melting of ice, and now even more particularly, when should that ice melt? Only during the reaction. So we fill this up with ice, and I hold it here. Let's say it's got ice in it. We've got our water all the way up there. We can see everything nice and neatly. Okay? What happens? Room temperature means heat transfer. What happens to the ice? It melts. What happens to the volume? It drops. Uh-oh. That's our standard state, is the volume dropping. We only want the volume to drop when the experiment is actually running. Okay, so that's another problem with this. We can't control or prevent that ice from dropping. We can minimize it as much as we can. How can we prevent the ice from melting inside this container? We'll surround it with even more ice. Okay, so when you set up your experiment, you're going to bury this reaction container in a whole bunch of ice. The hope is that that way you keep it thermally isolated, and the ice inside only melts due to the reaction heating it up from the inside. Okay, that's our hope. Because it's only a hope and that's not actually going to happen, what we're going to have to do is be very careful with our experiment. Okay? So ideally what we would see for our temperature plot is we would have time and volume. Our volume would start at the top and it would be a flat line. Right? We'd collect data points and we'd have a straight line at the top because the ice is not melting. Then the reaction occurs. What happens to the volume of the ice? Decreases, or volume, total volume decreases, and we see a sharp drop. Let's say it goes perfectly. Reactions instantaneous transfer of heat, instantaneous phase changes. So we're going with the extreme ideal circumstance. The reaction's done, no more heat is transferred, what happens to the volume? Flat lines. So when we go through to determine our change in volume, what do? We just take the difference. Great, nice and easy. Except, let's take a look a little bit more of what your experiment's probably going to look like. Let's draw it here in orange. You're going to start probably about the same time, okay? Except more than likely your experiment's not going to flatline. We'll have a slight slope on it. Okay, so very slight there. We start the reaction, and what happens? It's not going to happen instantaneously. It's going to take some time. So it's going to slowly start to decrease until eventually what happens? Slowly stops happening because it's a rate, and you'll probably see something along those lines. I know that's a little shaky, but it's close. Where was your initial volume? Okay, well, your initial volume should occur where? Up here? No, where should it occur? As soon as you started the experiment. So we'll circle these in green. So we can say here. Where's our final volume? The end of the reaction. Where's the end of the reaction? Where did it flatline? Yeah, it's kind of crappy, isn't it? So that's what we're going to have to try and build a way to kind of get around. So in the course of this, your procedure says you will record times for 5 minutes after you start the reaction. Okay? I want you to record for 10 minutes after the reaction starts. Okay? This will help us interpret the data later on if we extend this time out. Okay? What we're hoping for is that we can see that flat line. We're probably not going to get that flat line, but we're going to hope to get it somewhat flat. Okay? The next issue, in this dropping, in this middle area, so let's arbitrarily decide that this is the end of the reaction. Okay? And we could try and go through and just say final minus initial with those volumes. Except, what's happening in that beginning point? Is it staying as a flat line? No. The ice is melting, which means in the course of during the reaction, the ice is melting due to the reaction, but it's also melting due to ice melting. Okay? So we need to account for that extra bit of energy that isn't part of our experiment. So what we need to do is come up with some way to normalize that out or average that data out. So what we're going to do is fit two equations of fit two lines to it. You're going to fit a line to the beginning of your data, which means you need enough data at the beginning to actually have a straight line. Okay? How many points do you need for a straight line? Absolutely minimal, 2, but what if one of those data points is wrong? You need something to average with. Minimum to average, you need 3. To get a reasonable average, we're going to jump that up. I want at least 10 data points before you start the experiment. Okay? This will allow us to get a fairly clean straight line off of that. Okay? And we can have Excel fit that line for us. Those 10 data points do not need to be 30 seconds apart. If you want to do 15 seconds apart, I'm fine with that too. Just make sure you record to the full accuracy of your instrument. Okay? Next part. We'll run our experiment for 10 minutes. We need to figure out where our final temperature is. So we may be able to now account for our initial volume, but our final volume is a bit tricky. Okay? So what we're going to do for our final volume is very similar. We'll probably take the last 5 to 10 data points, regardless of what your data shows, and fit a straight line to that. In theory, what's the relationship between those two lines? They should be parallel, because what we've done is now accounted for the ice melting on its own. Both in our initial value and our final value, our lines should be perfectly parallel. They're not going to be. Okay? So what we need to do is come up with some way to account for that. To do that, we will go through and determine a change in volume at 3 different values along this graph. We will pick a time where we decide, you know what, that's where I'm going to arbitrarily decide that's the end of my reaction. And I will calculate a change in volume there. How do we get that change in volume? We know the time value. If we use a fitting program, we'll know the equation of this line. What would the y value be at this point? Substitute your x value into your equation of the line. You now have a y value. What you'll do, you'll take that same time value and now plug it into your other equation of the line, which gives you your y point for your initial. Take the difference, you now have a change in volume. Okay? If you take a look at the example procedure or the example calculations in that lab report, he does show that. It's just not very clear that that's what he's doing. There's a big string of numbers with like infinite sig figs. It's a bit ridiculous. That's what he's trying to show. Okay? But that one calculation is probably not very correct, so we will arbitrarily pick another difference. And we'll pick another point. With these changes in volume, we'll now have 3 changes in volume. We can go back, so now I'm going to delete this, just so you know, it's going to disappear here. We'll go back to our calculations. We know the change in volume for 3 different circumstances. We can calculate the change in mass for each of those 3 circumstances. Once we have the change in mass, we can go back even further to calculate the heat transferred for each of those 3 circumstances. Now you can average those values. Okay? So what we did is worked our calculations pretty much backwards. We went from our end result and went all the way to where we're actually going to start our calculations. Okay? So we'll talk through it kind of real briefly here at the very end. This is an example of what you'll get for your results. You'll plot your volume and your time. Oh, we've been going. Oh, not that one. You want to fit the equation of a straight line to your first part of the data, so the beginning part of the data, and you want to fit it to just, oh, this one didn't show it, the end part of your data. There is an equation of a line running through here, just a bad copy-paste. Okay? He's got the equation of the line shown for the bottom one and the one shown for the top. We decide to arbitrarily pick some time value. We plug that time value into the equation. That gives us our final volume. We pick that same time value, plug it into the equation for our initial volume, figure out our initial volume. The difference gives us our change in volume. Once we have the change in volume, see if I remember these correctly. We know the change in volume, just to give you an estimate. In theory, if everything worked perfectly, you should have something like a change in volume of 0.6 milliliters. More than likely, you're going to be on the order of 0.4 milliliters as far as a change in volume. We know that is equal to, I'm going to do the substitution, the negative change in mass of the water over, the density of ice plus the change in mass of water over the density of water. This is a substitution. I think I did the substitution correctly. So this is not the same as what was shown up there. This is after you substitute in what the change in mass, relationship between the change in mass of ice and water. Okay? At this point, you only have one variable. You have the change in mass of the water. You can solve for the change in mass of the water. Numbers. I don't have an example number anywhere close to the top of my head for this. Well, we'll just guess. Let's say it's 2 grams. So this is a random number. 2 grams is your change in mass in the process of this reaction. We now want to determine the heat released. The heat will be our change in mass, which is our 2 grams, times our enthalpy change, okay, our enthalpy of fusion. If we're going to use grams, we want the enthalpy change in units of grams. I believe it is 6.01 kilojoules per gram of water. This gives us the heat absorbed by the ice. To determine the heat released, what would we do? You could plug it into the equation, but according to our equation, we only had 2 terms. Heat released plus heat absorbed is 0. If this is heat released or heat absorbed, first off, our sign should be positive because it was absorbed. It was a reactant in that process, which means our heat released should be just the opposite. It will be the negative of that value. Okay? That gives you the heat released in the course of the experiment that you ran. We want the enthalpy for the reaction. So what you'll have to do is then convert your grams of, or your kilojoules per gram into kilojoules per mole and that's going to be, you have to be careful with that. You have to make sure that it's for your limiting reagent. Okay, all sorts of little steps with this. Again, trust me, it's a little bit easier once you actually have numbers to work with. Okay, the experiment is done relatively fast. There is at least one computer here for you to enter numbers into. So you can go ahead and use Excel here, and I can show you how to fit data within Excel. In fact, I think I'm going to do that almost right now. Okay, so that you guys know how to get some of this information.
The top right corner, that's delta mass of
Water.
water over the
Yeah.
density of water.
Over the density of water. Yeah. Okay. So experimental issues. Last things that we kind of want to cover here. Our sulfuric acid. Sulfuric acid is corrosive. Please be careful with it. Don't burn yourself. The reaction, we want to go as efficiently and smoothly as possible. So we want to maximize surface area contact between our sulfuric acid and the magnesium. So what could we do to maximize that interaction? What's that? We could try and liquefy everything. So the sulfuric acid will for sure be a liquid, but magnesium is a solid. We can't liquefy the magnesium because that's really expensive. So we could cut it into smaller pieces to maximize that surface area. Okay? The problem with small pieces is that they will get stuck on the sides of the glass. So if you cut them up into smaller pieces, just make sure that you get all of the magnesium into the bottom of the reaction. Okay? The other issue with the magnesium is it is also fairly reactive. Will react with water and oxygen in the air to form another material. That material is a coating on top of the magnesium. That coating does not react with sulfuric acid, and it prevents the sulfuric acid from reacting with the actual magnesium. So what can we do to eliminate that? We can scrape that material off. So you can use the steel wool to kind of roughly polish or score the magnesium so that you expose more of that fresh magnesium surface. Okay? Next issues to address. We want the reaction to mix as evenly as possible to maximize that heat transfer. We don't want the reaction to be slow. We want it to go as fast as possible to get all of that heat out into the ice. Okay? Problem with that. Okay? We've got two phases, a solid and a liquid. The only place they interact is at the surface area, or the surface of the solid. So we can cut up the pieces. How else can we maximize the interaction between them? We could stir it. Okay, so we get a stir rod in there and stir that around. Except we've got another issue if we do that. Heat transfers into the stir rod. We don't measure that. So we would have to assume that heat transfer is relatively minimal. Okay? Another big issue, this top is open, which means heat and potentially water vapor can go out the top. So let's fix that problem. Let's cork it. Right? That does trap the heat in there. What else does it trap in there? The hydrogen gas that's also formed in the course of the reaction. Not a good idea. We'd get flying corks everywhere if someone poked their eye out. Okay? So we won't end up corking it. Be aware that that's a source of error. Okay? I think I covered everything there. Sorry, what was your question?
A few slides back when you did the balance calculation, you had hydrochloric acid in there, so you changed the whole equation.
Yes, so that whole equation is wrong. We can go back and fix it. It actually gets easier. Because in this equation, we've got a 2 floating in front of that sulfuric acid, or hydrochloric acid. If we make it H2SO4, what's the coefficients throughout the equation? 1. So it makes all of your calculations a lot easier, actually, to use sulfuric acid instead of hydrochloric acid. But yes, thank you for pointing that out. All calculations, fun. Results and calculations in the lab report. Okay, so what I want to see is your graph of data. First group to give me or to enter all of their data into Excel up here, I will go through and show, and actually I'll tag it on as an extra recording, how to get Excel to, tagging on as an extra recording is not going to work. We'll do it in my computer. How to actually get Excel to plot trend lines for certain sections of data, which is ultimately what you need to be able to do this. You need those trend lines. So if you're going to use a graphing program like Excel, Numbers if you're using Max, or OpenOffice, I think all three of those have the exact same rules behind how you would set up the trend lines. Mesa has a site license to graphical analysis, which does some of this stuff a little bit easier. Unfortunately, I don't know how to use it appropriately, which means if you're going to use graphical analysis, you're kind of on your own as far as generating data and analyzing it. I'll still help you with it, but we'll be kind of guessing and checking as we go through and do it. Okay? So first group to finish, get all of your time and volume measurements. Will come in, enter their data onto my laptop, and then I will walk through with that group and record how to get the trend lines all put onto the data or all into Excel so that you know how to do it for your experiment. Okay? So we'll go ahead and get started. That's a lie. Sorry, I want to talk through this real quickly because otherwise I'll have to tell everybody about it. The procedure is very, very confusing. First thing you're going to do is get your calorimeter. You're going to fill it with water, all the way with water, and then you're going to put the cork in. What happens when you put the cork in? All the water is going to spray out either the sides or out the top. So when you do this, please wear your goggles. It will spray water out the top depending on how hard you push it in. That cork needs to get pushed into the point where it's now closed in there. Air cannot come in or out. In theory, there's no air in there to begin with. Okay? What you'll then do is add water in this larger tube. Okay? We need water in the small pipette. So we talked about in lecture today, water is going to equilibrate. If there's no water in here, can we get water into here? No. So we'll fill this up with water so that the water level roughly matches. You can then close the system. If everything is done properly and this cork is properly seated, what should happen to the volume of the water here? It should stay exactly the same. So the first page in your procedure asks you to do just that. That's all it's doing. The next part of it, it says to go through, pull it out, which may take a little bit of effort because you have to jam it in there pretty hard. Fill your beaker with as much ice as you possibly can. Then fill it with water. You'll then go through and do the same thing. Push the cork back in. You're still going to get a spraying mess everywhere. That's fine. Okay? Open that up again. Fill it up again with water and close it. Okay? At this point, you might see the volume change. Why? The ice is already starting to melt. What we want to do is prevent that ice from melting. So what should we do? Now we'll put it in a thermal isolation by wrapping it in that ice jacket. Okay, so you'll get a large bucket. You'll put this into the bucket somewhere near the top and pack ice all the way around it. Okay, ice should mound all the way up. Give it some time to just kind of chill on its own for a little bit. Then go through, do the closing process, and look at your volume. If the volume is still dropping, that's because there's an air leak. Push harder on the cork, okay, to get it set into there. Okay? Then close it and watch it again. If it's still dropping, you still have an air leak, you're going to still have to try and figure out where that air leak is coming from and prevent that from occurring. Okay? You might also see it increase as it happened in class. Why would it increase? That was a little bit trickier. Why would pressure cause it to increase? That pressure has to come from somewhere. That pressure is coming from air. Where's that air located? Inside the beaker. No air should ever be inside the beaker. Ice and water only. No air. Okay? So make sure when you set up your experiment that there is no air in there. Okay? Once it looks like it's roughly stable, you're more than welcome to call me over to check and verify that it's stable. I'll probably say it's fine, regardless of what you think. and then you can go through and actually set up with your reaction. The sulfuric acid you'll want to keep in an ice bath, either in your large bucket with this, or in a separate ice container. We want the sulfuric acid to be nice and cold so that when we add it to the reaction tube, we don't get a heat transfer and lose some of that ice. Okay? You'll add the sulfuric acid into your reaction tube. Now you can start monitoring your volume for 10 data points. Once you've got the 10 data points, you can now add the magnesium in and record for 10 minutes, every 30 seconds. Okay? At the end of those 10 minutes, you're done with the experiment, clean everything up. The reaction mixture goes where? Into the waste. All the ice and water can go into the drain. Okay? We aren't going to worry too much about that because you didn't spill. If you spilled, where does it go? It goes into the waste. Okay? So at any point, if you contaminate your ice or water, then it has to go into the waste. Otherwise, down the drain. Okay? Questions about that? Okay. Good luck. If you got questions in there, just ask. Partners. Or you can do it by yourself too, but partners is easy.